Inside Boeing and Airbus boardrooms, one assumption has held steady for decades. The tube and wing design is the only way to move hundreds of people across oceans profitably. But a few years ago, something subtle changed. Inside internal reviews and closed technical discussions, this assumption stopped being treated as settled. Engineers who normally dismiss unconventional layouts began running deeper simulations. Airline planners stopped labeling the idea as impractical, and regulators started asking questions they had never asked before. So what changed? This wasn't a one-off test. This was the moment assumptions stopped holding. Because buried inside this reaction was a problem that Boeing and Airbus have spent decades avoiding. The cylindrical fuselage you board every time you fly, it's dead weight. It creates drag, burns fuel, and contributes nothing to keeping the plane in the air. What if everything, passengers, cargo, fuel tanks, became part of the wing itself? So what happens when the part of the airplane that was never meant to lift suddenly does? And what kind of design forces the industry to reconsider rules it has relied on for generations? In 2019, Dutch airline KLM and researchers at Delft University of Technology unveiled something that made aerospace engineers do a double take. They called it the Flying V. Not a concept sketch, a genuine engineering project with real funding, real timelines, and real stakes backed by one of the world's leading airlines and one of Europe's most prestigious technical universities. Picture a boomerang scaled up to carry 314 people across the Atlantic. That's the Flying V. From above, it's a wide V-shaped structure with engines at the rear, not hanging under the wings. The nose is flattened and broad. Passengers sit inside the wings themselves. It represents a fundamental reimagining of flight, challenging assumptions that have governed aircraft design since the dawn of the jet age. But here's the uncomfortable truth Boeing and Airbus don't want discussed. If this design delivers on its promises, it makes every 777, every A350, every wide-body jet currently in service look inefficient by comparison. And inefficiency in aviation isn't just an engineering problem. It's a financial death sentence. Let's talk about something you've probably never thought about. The tube you sit in when you fly, it's aerodynamically useless. Traditional aircraft separate everything into distinct parts. A cylindrical fuselage for passengers and cargo, wings for lift, a tail for stability. This design has worked for nearly a century, but it comes with massive inefficiency. The fuselage creates drag without generating any lift. It's dead weight from an aerodynamic perspective, a necessary evil in conventional designs. Airlines burn thousands of tons of fuel dragging this tube through the sky. Fuel accounts for 30 to 40% of an airline's operating costs. A Boeing 777-300ER burns roughly 6.8 to 7.8 metric tons of fuel per hour. That's the weight of about 5 full-size cars being consumed every single hour. Multiply that across thousands of flights per year, and you're looking at billions in fuel costs spent pulling a tube through the air that does nothing to keep the plane flying. The Flying V eliminates this problem. Instead of separating the fuselage from the wings, it integrates everything into a single V-shaped lifting body. Every square inch of the aircraft surface contributes to keeping it in the air. Nothing is just along for the ride. So how does a plane shaped like a boomerang actually fly? From above, the Flying V looks like an enormous arrowhead slicing through the sky. The engines are mounted at the rear of the V's arms. The passenger cabin follows the contour of the wing roots, creating an interior space unlike anything in commercial aviation today. Every aspect serves a specific aerodynamic purpose. The blended wing body design means the entire structure generates lift, not just the wings. The result, according to KLM's computer modeling and wind tunnel testing, is staggering. A potential reduction in fuel consumption of 20% compared to a similarly sized Boeing 777. In an industry where engineers celebrate 2% efficiency gains, this is enormous. The Flying V carries approximately 314 passengers with a range of 4,000 nautical miles, suitable for most long-haul routes. Same capacity, same range, 20% less fuel. The efficiency gains go deeper. In conventional aircraft, fuel stored in the wings creates bending moments that require heavy wing structures to resist. The Flying V distributes fuel tanks across both the wings and central fuselage area, creating balanced mass distribution. This reduces structural stresses, allowing lighter structures without compromising safety. Lighter structures mean less fuel needed, creating even more efficiency gains. Even the tail breaks with tradition. Instead of a familiar vertical stabilizer, the Flying V employs a small T-tail at the apex of the V shape. Because the entire structure generates lift, The Flying V produces more lift per unit of wing area than conventional designs. The aircraft could potentially operate from shorter runways or carry heavier payloads over the same distances. Now let's talk about why this matters to airlines, and why Boeing and Airbus executives are paying attention. That 20% fuel reduction isn't just impressive on paper. For a single Boeing 777 flying long-haul routes, burning 6.8 metric tons of fuel per hour, a 20% reduction means saving roughly 1.4 tons per hour. Over a 12-hour transatlantic flight, that's nearly 17 tons of fuel saved per flight. Multiply that across an airline's entire fleet, making thousands of flights per year, and you're looking at hundreds of millions in fuel cost savings annually. Let's use real numbers. Jet fuel costs around $800 per metric ton. Saving 17 tons per transatlantic flight equals roughly $13,600 saved per flight. An airline operating just 10 transatlantic routes per day saves $136,000 daily. And this is the moment airline planners stop asking whether a design is unconventional and start asking why it is not already mandatory. That's over $49 million per year from 10 routes alone. But the pressure isn't just financial. Aviation is responsible for about 2 to 3% of global carbon dioxide emissions. Airlines face increasing pressure from regulators, environmentally conscious passengers, and corporate sustainability goals. The European Union has introduced carbon pricing mechanisms. Passengers are choosing airlines based on sustainability commitments. The Flying V's 20% fuel reduction translates directly into a 20% reduction in CO2 emissions per flight. For airlines facing carbon taxes and sustainability mandates, this isn't just a cost saver. It's a regulatory advantage, a marketing advantage, a competitive advantage. Manufacturing efficiency adds another layer. The Flying V's integrated wing structure reduces wing bending loads, meaning less material is required to achieve the same strength. This potentially lowers overall aircraft weight by 15 to 20% compared to traditional designs. Lighter aircraft need less fuel. Lower operating costs mean better profit margins. Here's where it gets uncomfortable for Boeing and Airbus. These companies have spent decades perfecting the tube and wing design. Their supply chains, manufacturing facilities, and engineering expertise are all built around this configuration. Billions invested in tooling and processes optimized for cylindrical fuselages. The Flying V threatens to make that expertise less competitive. In an industry with only 2 major players, that's an existential concern. If airlines start demanding V-shaped aircraft because the economics are better, legacy manufacturers face a choice: adapt or lose market share. Adaptation means retooling factories, retraining engineers, rebuilding supply chains. It means admitting the design philosophy they've defended for decades has a superior alternative. But fuel savings mean nothing if passengers refuse to board the plane. So what's it actually like inside a Flying V? The passenger cabin occupies the central portion of the V shape, measuring roughly 10 to 12 feet wide at its widest point. Seating is arranged in a 2-2-2 configuration. But here's something remarkable. Every passenger could potentially have a window seat. The V-shape naturally creates more exterior surface area per passenger than a cylindrical fuselage. The cabin's slight slope makes the space feel more open and less claustrophobic than traditional tube cabins. The rear-mounted engines deliver on their promise of reduced noise. By pushing engines to the rear, the Flying V puts maximum distance between the noise source and passengers' ears. Imagine crossing the Atlantic in near silence, able to hold normal conversations without raising your voice, without the constant background drone. Engineers have rethought emergency exits, evacuation slides, and passenger flow. Computer simulations show solutions exist for all these challenges. Lighting, ventilation, emergency evacuation procedures have all been modeled to ensure compliance with stringent safety regulations despite the V-shaped design. In terms of service, airlines could theoretically adapt existing Boeing 777 type catering and maintenance procedures to the Flying V, reducing operational learning curves. It's a design that combines radical aerodynamics with practical airline operations. But all of this was just theory until September 2020. That's when things got real. At an A base in Germany, engineers from KLM, Delft University, and Airbus prepared for the first flight test of a Flying V-scale model. The model weighed 22.5 kilograms and measured 3 meters wide. Large enough to validate aerodynamic principles and flight characteristics. Large enough to prove whether the computer models were right. The model accelerated down the runway and lifted off at 80 kilometers per hour. Engineers had worried about rotation during takeoff. It didn't create problems. The model climbed smoothly and maintained stable flight. During the test flight, the Flying V demonstrated better characteristics than expected. The blended wing design proved inherently stable because the lifting surfaces are continuous. Lift is generated along the entire structure. The model maintained smooth flight with reduced wing flex and lower aerodynamic drag. Landing was slightly unconventional. The model landed with a slightly nose-high attitude, similar to the Concorde's landing profile. But it worked. The test was declared a success. Here's what makes this significant. Airbus was involved. One of the world's two dominant aircraft manufacturers participated in testing a design that could potentially challenge their own products. Airbus builds the A350, one of the most advanced wide-body jets in service. Yet they are collaborating on a project that could make those designs obsolete. That's recognition this concept has genuine potential. This isn't a fringe experiment. It's a serious engineering project backed by major industry players who see potential in fundamentally rethinking aircraft design. They are involved because the math works, the aerodynamics work, and the economics are too compelling to ignore. But before you book a ticket on a Flying V, there are serious obstacles to overcome. First, certification. Civil aviation authorities like EASA and the FAA have decades of experience certifying tube and wing designs. Their certification standards and safety requirements are all built around conventional aircraft configurations. The Flying V is different. Convincing regulators this aircraft is safe in all conditions will take extensive testing and flight data. This process could easily take a decade or more and require billions of dollars in investment. Second, airport infrastructure. Every airport is designed for conventional fuselages. Boarding bridges, ground handling equipment, cargo loaders, all assume a certain aircraft geometry. Airports would need to modify equipment to accommodate the V-shaped layout. These adaptations represent upfront costs that airlines and airports may hesitate to absorb. Smaller regional airports might struggle to make modifications, potentially limiting where the Flying V could initially operate. Third, passenger psychology. Humans are creatures of habit. We're used to the cylindrical fuselage cabin experience. The Flying V cabin is different. The slope creates a cabin wider at the root and narrower toward the tips. Some passengers might feel uneasy, especially where the cabin narrows. Airlines would need to invest heavily in cabin design to make the interior feel familiar and comfortable. The first few years would be critical in establishing passenger confidence. Finally, maintenance and training. Maintenance crews would require specialized training to handle systems distributed across the V-shaped wings. Mechanics trained on 777s can't just start working on Flying Vs without extensive retraining. New maintenance protocols would need to be developed from scratch. Pilots face the same challenge. The Flying V flies differently than anything currently in service. Pilots would need entirely new type ratings and training programs. This isn't insurmountable, but it's expensive and time-consuming. Here's what keeps Boeing and Airbus executives up at night. If the Flying V delivers on its 20% fuel savings in real-world operations, airlines will demand it. Not request it. Demand it. Because in an industry where profit margins are razor-thin and fuel costs can make or break quarterly earnings, a 20% efficiency advantage isn't a nice-to-have feature. It's a competitive necessity. And when airlines start demanding V-shaped aircraft, everything shifts. Airport infrastructure gets retrofitted. Maintenance protocols get rewritten. Pilot training programs get overhauled. The entire aerospace supply chain, worth hundreds of billions of dollars, begins optimizing for a different shape. Boeing and Airbus have spent nearly a century perfecting the tube and wing design. Their factories, their suppliers, their engineering teams, all of it is built around this configuration. The Flying V threatens to make that expertise, all those decades of refinement, less valuable. Not worthless, but less competitive. And in an industry with only two major players, that's an existential concern. This isn't about one experimental aircraft. It's about whether the fundamental design philosophy that has dominated commercial aviation since the 1950s remains the best solution for the next 50 years. And right now, the answer isn't as certain as it used to be. But let's be clear about where we actually are. The Flying V isn't in service. It won't be for years, possibly over a decade. Certification alone could take 10 years and billions in investment. Airports would need to retrofit infrastructure. Smaller regional hubs might not be able to afford the modifications, limiting where this plane can even land in its early years. And passengers will need convincing. The first airline to operate the Flying V will be taking a risk. If passengers feel uncomfortable in the V-shaped cabin, if the novelty creates hesitation, That's a marketing problem that could tank adoption regardless of how good the economics look on paper. Maintenance crews will need specialized training. Pilots will need entirely new type ratings. Supply chains will need to adapt. None of this happens quickly in aviation. The industry moves slowly for good reasons. Safety, reliability, and proven track records matter more than innovation for its own sake. But dismissing the Flying V would be a mistake. KLM isn't funding this for headlines. Delft University isn't dedicating years of research for academic curiosity. Airbus isn't collaborating on test flights for fun. The test flight in 2020 worked. The aerodynamic modeling works. The economics work. And in an industry where 2 to 3% efficiency gains are celebrated as major achievements, a 20% improvement is a seismic shift. The Flying V will not replace the 777 or the A350 tomorrow, but it has already done something more disruptive. It has forced the industry to admit that the tube and wing design is not inevitable. And once that admission is made, the next aircraft Boeing or Airbus builds will not be judged against the past, but against a shape that no longer needs a fuselage at all. So here's the real question. If a plane is quieter, cleaner, and far cheaper to operate, does familiarity still matter? Drop a comment and let me know if you would trust a V-shaped aircraft on a long-haul flight. And if you want more deep analysis on aviation and engineering shifts like this, make sure to subscribe.